Enceladus is hiding something, and it's not being subtle about it. This moon, barely 500 kilometers across, a frozen snowball orbiting Saturn, is shooting columns of water into space. Not occasionally, not gently. Geysers of liquid water erupting through cracks in the ice at roughly 1,300 kilometers hour, blasting material so high that it escapes the moon's gravity entirely and feeds one of Saturn's rings. A world that's small should be cold, dead, and geologically silent. It should be silent. It should be dead. Instead, it's erupting. Enceladus is tiny, only about 500 kilometers wide. You could drive across it in a few hours. It orbits Saturn at a distance where sunlight is weak and temperatures average around -200 degrees Celsius. By every basic rule of planetary science, this world should be nothing more than an icy rock drifting through space. But it isn't. From deep fractures near its south pole, Enceladus fires massive plumes of water into space at speeds over 1,000 kilometers per hour. Not vapor mist, not frost. Entire columns of ocean material blasting hundreds of kilometers above the surface. Some of that material escapes the moon completely and feeds Saturn's faint E-ring. This moon is building a planetary ring right now, and that should not be possible. For over 200 years after its discovery in 1789 by William Herschel, Enceladus was barely worth mentioning. Textbooks gave it a paragraph at best. Titan got the attention. Europa got the headlines. Enceladus was background noise. That changed in 2005. When NASA's Cassini spacecraft flew past the moon, its instruments detected something strange. The magnetic environment around Enceladus was disturbed, bent out of shape. That usually means one thing: active material is escaping into space. Then Cassini's cameras confirmed it. 4 massive fractures at the South Pole were glowing warmer than the surrounding terrain. From those cracks, enormous jets of water vapor and ice particles were erupting continuously. Scientists nicknamed them the Tiger Stripes. Baghdad, Damascus, Cairo, Alexandria, each one a wound in the ice, each one venting an ocean. Here's the problem. Enceladus is small. Too small to hold on to heat from its formation, too far from the sun to absorb meaningful solar energy. It should have frozen solid billions of years ago. So what's keeping it alive? The answer is tidal heating. Enceladus doesn't orbit Saturn in a perfect circle. Its path is slightly elliptical, pulled and stretched by Saturn's gravity and nudged by a neighboring moon called Dione. As Enceladus moves along this orbit, Saturn's gravity squeezes and relaxes it over and over again. Imagine bending a metal wire repeatedly. It heats up at the stress point. The same thing happens inside Enceladus. Except instead of a wire, it's an entire moon being flexed by a gas giant 95 times the mass of Earth. That friction generates heat. Enough heat to keep a global ocean liquid beneath the ice. Cassini didn't just see the plumes. It measured gravity. During close flybys, subtle changes in the spacecraft's motion revealed something extraordinary. Beneath the ice shell, which may be as thin as 5 kilometers near the South Pole, lies a global ocean roughly 30 kilometers deep. Not a small pocket, not a regional lake, a planet-wide ocean wrapped around a rocky core. And that detail changes everything, because this ocean isn't isolated from rock. It touches the core. And where water meets rock, chemistry happens. In 2015, Cassini flew directly through one of the plumes. It sampled the spray. What it found shocked researchers. Water vapor, carbon dioxide, methane, ammonia, complex organic molecules, and most importantly, molecular hydrogen. On Earth, molecular hydrogen in ocean water is commonly produced by a process called serpentinization. That's when hot water reacts with minerals in rock. The reaction releases hydrogen and chemical energy. That chemical energy feeds hydrothermal vent ecosystems on our ocean floors. Entire communities of life exist there without sunlight. No photosynthesis, no surface energy, just chemistry. Finding hydrogen on Enceladus strongly suggests similar hydrothermal activity may be happening right now on its ocean floor. Then came another clue. Cassini detected tiny grains of silica in Saturn's E-ring. These nanoparticles can form only in very hot water interacting with rock above about 90 degrees Celsius. That means parts of Enceladus's ocean floor may be surprisingly warm. Warm water, rock interaction, chemical energy. That's a powerful combination. For years, one major ingredient for life was unconfirmed: phosphorus. In 2023, researchers reanalyzed Cassini data and found sodium phosphates in ice grains from the plumes, at concentrations higher than Earth's oceans. Phosphorus is essential. It forms the backbone of DNA and RNA. It's central to cellular energy systems. With that discovery, Enceladus officially checked every box on the habitability list: liquid water heat source, organic molecules, chemical energy rock-water interaction, essential elements, tolerable pH conditions, everything required for life as we understand it. Everything, except proof of biology. Here's what makes this unsettling. Enceladus is practically offering samples. The ocean is spraying itself into space. We don't need to drill. We don't need submarines. We just need to fly through the plume with advanced instruments. But Cassini wasn't designed to search for life. Its tools were built decades ago to analyze atmospheres, not detect biological signatures. It could see complex chemistry. It could not tell us whether that chemistry is alive. Several proposed missions have aimed to return: dedicated plume samplers, orbiters, even landers. None are currently approved. Meanwhile, the moon keeps erupting. In 2017, NASA made a difficult decision. They intentionally crashed Cassini into Saturn. Not because it failed, but because they were afraid. Afraid that one day the spacecraft might accidentally collide with Enceladus or Titan and contaminate those oceans with Earth microbes. If terrestrial bacteria reached that ocean, we might never know whether future discoveries were native or contamination. We protected the experiment by destroying our own spacecraft. That tells you how serious this is. If we confirm even microscopic life in that ocean, the consequences would be enormous. It would mean life is not unique to Earth. It would mean that when water, chemistry, and energy exist together long enough, biology emerges. That would dramatically increase the probability of life throughout the galaxy. But there's another possibility. If Enceladus has every ingredient and still has no life, that's equally profound. It would mean the jump from chemistry to biology is far rarer than we imagined. Either outcome reshapes science. Enceladus is 1.4 billion kilometers away, but that's not the real barrier. The real barrier is time, funding, and political will. To reach that ocean directly would require drilling kilometers through ice on another world. That means decades of development. So for now, we wait. And while we wait, plumes of ocean water continue blasting into space. Warm, chemically active, potentially alive. A tiny moon orbiting Saturn may be holding the answer to one of the biggest questions humanity has ever asked. And right now, it's whispering. The question is whether we choose to listen. Imagine a small moon, so cold and silent it seems lifeless. Yet this moon is erupting. Enceladus, with a mere 500 kilometers diameter, orbits Saturn. Here, sunlight is weak and temperatures plummet to minus 200 degrees Celsius. By conventional wisdom, one would expect Enceladus to be just an icy rock. But it is anything but that. From its south pole, Enceladus shoots massive plumes of water into space at over 1,000 kilometers per hour. These are not mere mists. They are columns of ocean material exploding hundreds of kilometers above its surface, feeding Saturn's faint E-ring. For over 200 years, Enceladus was a background character in the solar system. But this changed dramatically in 2005 when NASA's Cassini spacecraft revealed its secrets. It detected disturbances in the magnetic field around Enceladus, suggesting that active material was escaping into space. Cassini's cameras picked up 4 significant cracks, known as the tiger stripes at the South Pole. These fractures were warmer than the surrounding ice, continuously venting water vapor and ice particles. So, how can this tiny moon be so active? The answer lies in tidal heating. Enceladus orbits Saturn in an elliptical path, pulled by Saturn's gravity and affected by the neighboring moon, Dione. As it moves, the gravitational forces squeeze and stretch Enceladus, generating heat. Think of bending a metal wire. It heats up. This heat prevents the moon from freezing solid, keeping a global ocean liquid beneath its icy surface. Cassini didn't just discover plumes, it measured the moon's gravity too. During close flybys, scientists found a global ocean approximately 30 kilometers deep beneath the ice. This ocean interacts with the rocky core of Enceladus. Wherever water meets rock, chemistry occurs. In 2015, Cassini flew through one plume and found water vapor, carbon dioxide, methane, ammonia, and even molecular hydrogen. On Earth, hydrogen forms during serpentinization, where hot water reacts with rocks, creating chemical energy essential for life. Finding hydrogen suggests possible hydrothermal activity on Enceladus's ocean floor. Further analysis revealed tiny grains of silica, which form only in very hot water interacting with rock. This indicates that parts of the ocean floor may be quite warm, creating a hospitable environment for life. Phosphorus, a crucial element for life, was confirmed in 2023. Researchers found sodium phosphates in ice grains from the plumes at concentrations higher than Earth's oceans. With liquid water, heat sources, organic molecules, chemical energy, and essential elements, Enceladus meets all the criteria for habitability. However, proof of biological life remains elusive. Cassini, while revealing complex chemistry, wasn't equipped to detect life. Several proposed missions have sought to explore further, but none have been approved so far. In 2017, NASA crashed Cassini into Saturn to prevent contamination. They were concerned that earthly microbes could reach Enceladus's ocean, muddling future discoveries. This highlights the seriousness of the search for life. If we find even microscopic life on Enceladus, it would mean life is more common throughout the galaxy. Conversely, if all ingredients for life are present yet no life exists, it suggests the leap from chemistry to biology is far rarer than we think. Enceladus is about 1.4 billion kilometers away. However, the real barriers are time, funding, and political will. Reaching its ocean directly would require extensive drilling through ice, taking decades to develop. For now, we wait as plumes of potentially life-sustaining water continue blasting into space. This tiny moon may hold the answers to profound questions about life in the universe. Will we choose to listen to what Enceladus is whispering? Stay tuned for more discoveries.